a 30-minute documentary narration by Richard C.J. Young, C. Jung. Part 1. The idea that keeps coming back. The artificial gill is one of those ideas that refuses to die. It surfaces every decade or so, in a patent filing, in a DARPA solicitation, in a university press release. And every time it surfaces, it arrives with the same basic promise: a device that pulls oxygen directly from seawater and delivers it to a human being, the way a fish does, without tanks, without surface supply, without a countdown clock. And every time it surfaces, it disappears. Not because the idea is wrong, because the execution was wrong. I want to be honest with you about this at the outset. I am not going to tell you this problem is solved. I am not going to tell you a working device exists, that a Navy SEAL has used one, or that the engineering is finished. It is not. What I am going to tell you is that there is a version of this idea that is not science fiction. A version built from components that exist today, that obeys the laws of physics as we understand them, and that has a specific, bounded first experiment that would tell us within 18 months whether it works at human scale. That is a different claim than "we invented a gill." It is a more honest claim, and I think it is a more interesting one. There is a number that frames this entire discussion, and I want you to hold it in your mind before we go any further. 47 minutes. That is the approximate bottom time a diver gets from a standard aluminum 80 cubic foot scuba cylinder at moderate exertion at 30 feet of depth. That number has not meaningfully changed since Jacques-Yves Cousteau and Émile Gagnon developed the modern demand regulator in 1943. 82 years of diving technology, lighter tanks, better regulators, dive computers, mixed gas protocols, rebreather systems, and the fundamental constraint is still the same. You are on a clock from the moment you enter the water, and the clock does not care about anything except how much gas you carried down with you. The artificial gill is the idea that would make that clock irrelevant. Not by giving you a bigger tank, by eliminating the tank entirely. Let me start where every serious engineer starts, with the people who tried before, and with exactly why they failed. Part 2. Everyone who tried before. The serious research history on artificial gills for human use is shorter than most people assume, and more instructive than most people acknowledge. The first credible attempt came out of the Aquanautics Corporation in the early 1980s, with backing from the US Office of Naval Research. Their approach used a cobalt-based shift-base compound, a synthetic oxygen carrier molecule, dissolved in a recirculating fluid loop. The chemistry was elegant in principle. The shift-base molecule would bind dissolved oxygen from seawater on one side of a membrane, transport it through the fluid loop, and release it on the other side, where it could be collected and delivered to a breathing circuit. The carrier molecule was the key innovation. It massively increased the oxygen transport capacity of the fluid compared to water alone, because the molecule actively grabbed oxygen molecules rather than passively dissolving them. The concept worked at small scale. They sustained small crustaceans and then small mammals in sealed chambers breathing only oxygen extracted from the water around them. The government was interested. The research was real. The results were published. This was not a garage project. It was funded federal research with peer-reviewed outputs. And then it stopped. The cobalt carrier compound degraded. Its oxygen binding capacity dropped off over time in a way that was not economically recoverable on any reasonable operational timeline. The molecule would bind oxygen, but the binding became less efficient with each cycle, and the degradation was irreversible. The compound that made the chemistry work was also the compound that made the device disposable after a few hours. You could not refill it. You could not regenerate it. You had to replace the entire carrier fluid charge. At the cost and scale required for a human-rated system, the economics did not close. A diver who needs to replace a several $100 fluid charge every 4 hours is not operating more efficiently than a diver who simply carries a bigger gas cylinder. The idea went back into the drawer. It came back in the early 2000s, this time in academic and patent literature, with a different approach. Instead of a synthetic carrier compound that degrades, researchers began exploring perfluorocarbon emulsions, PFC fluids, as the oxygen carrier. PFC fluids have a remarkable property. They dissolve oxygen at concentrations roughly 20 times higher than water at the same partial pressure. They have been used in medicine as blood substitutes and in liquid breathing research since the 1960s. The most famous public demonstration was a mouse submerged in a PFC fluid, saturated with oxygen, surviving by breathing the fluid directly. That experiment has been replicated many times. The chemistry is real. The critical difference between PFC and the cobalt shift base is stability. PFC fluids are chemically inert. They do not degrade. They do not lose oxygen binding capacity over time. They can be recirculated indefinitely. The degradation problem that killed the aquanautics approach simply does not exist with PFC. The fluid lasts as long as the hardware lasts. The membrane contactor technology, hollow fiber bundles that allow dissolved gas to transfer between a liquid on one side and a gas or second liquid on the other, had been refined significantly by industrial applications in the wine industry, the power generation sector, and water treatment. Companies like Liquicell and 3M had been manufacturing these modules at industrial scale for decades. The hardware existed. The carrier fluid existed. The basic chemistry was validated. So why does no device exist today? Because moving from the components work in a lab to the integrated system works at human metabolic demand, underwater, for 6 to 8 hours, reliably enough to trust your life to it, is an engineering distance that nobody has yet traveled. Not because it is theoretically impossible, because it is expensive. It requires solving several hard sub-problems simultaneously. Flow rate, power consumption, membrane fouling, gas buffer management, emergency redundancy, and because the market for the result, military diving applications specifically, is small enough that no private company has had the financial incentive to bear that development cost without government backing. The gap is not scientific. It is economic and organizational. That is a different kind of problem, and it has a different kind of solution. Part 3. What the physics actually requires. Before I describe the device, I want to walk through the physics honestly, because the numbers are where most versions of this story skip over the hard part. A resting human being consumes approximately 250 milliliters of oxygen per minute. A diver swimming against a current at moderate exertion consumes between 1.5 and 3 liters per minute, roughly 4 to 4.5 grams of pure oxygen every 60 seconds. At maximum exertion, swimming hard against a strong current, carrying equipment, that number can spike to 4 liters per minute or more. Seawater at the surface holds approximately 7 to 8 milligrams of dissolved oxygen per liter. That number drops slightly with depth and temperature changes, but 7 to 8 milligrams per liter is the working figure. It is worth pausing on how low that number is. A liter of air at sea level contains about 250 milligrams of oxygen. A liter of seawater contains about 8. The ratio is roughly 30 to 1. That is why fish have gills with enormous surface area, and why they pass enormous volumes of water across those gills continuously. A medium-sized tuna processes hundreds of liters of water per minute across its gill filaments to extract the oxygen it needs to sustain its metabolism. Do the arithmetic. To extract 4 grams of oxygen per minute from water carrying 8 milligrams per liter, you must process 500 liters of seawater every single minute. Not approximately. Exactly. That is the number the physics gives you, and the physics does not negotiate. And that is at 100% extraction efficiency, which no real membrane system achieves. At 40% extraction efficiency per pass, a realistic figure for a compact hollow fiber contactor, you need to process over 1,000 liters per minute to meet exertion demand. 500 to 1,000 liters per minute is not a small flow rate for a portable device. It is the flow rate of a moderately sized industrial pump. Moving that volume of water through a membrane extraction surface, in a package that a diver can wear or tow, with a battery that lasts 8 hours, is the central engineering challenge of this entire project. Everything else, the membrane chemistry, the carrier fluid, the rebreather loop, is secondary to the question of whether you can move that water volume with acceptable power consumption and acceptable device size. Here is what makes the number tractable rather than impossible. First, you do not need to extract 100% of the dissolved oxygen from every liter of water that passes through the system. The extraction efficiency of a well-designed hollow fiber membrane contactor in a PFC-assisted configuration is in the range of 40 to 60% per pass. That means at 60% efficiency, you need to process roughly 800 to 900 liters per minute to meet exertion demand, but only when the diver is at maximum exertion. At rest, the demand drops by a factor of 8 to 10. The system does not run at peak load continuously. A diver on a 6-hour mission is not swimming at maximum exertion for 6 hours. They are swimming at moderate exertion with periodic rest stops, current crossings, and work intervals. The average metabolic demand over the mission is probably 1 to 1.5 liters of oxygen per minute, not 3. That changes the required flow rate by a factor of 2 to 3. Second, the power requirement for an axial flow impeller moving 800 liters per minute through a compact low-resistance fiber bundle is on the order of 200 to 400 watts. That is a substantial power draw for a portable battery system, but it is not extraordinary. A modern lithium polymer battery pack with 4 kilowatt-hours of stored energy, a pack roughly the size of a car battery, weighing about 15 kilograms, can deliver 300 watts for over 10 hours. in a hydrodynamic sled housing underwater, with proper thermal management, that is a manageable package. Not as a vest. As a sled, the diver pulls behind them on a short umbilical. That distinction, vest versus sled, is the design decision that makes the physics tractable. The vest version of this device does not work at human exertion rates. You cannot fit a pump, a battery, and a membrane bundle large enough to process 800 liters per minute into something that sits on a diver's back without destroying their mobility and buoyancy. The sled version, with a proper battery pack and a properly sized pump, is within the envelope of what current hardware can deliver. The diver does not carry the system. The system carries itself, neutrally buoyant, and the diver pulls it like a trailer. Third, the dissolved oxygen extracted by the membrane contactor and carried in the PFC fluid must be stripped out of the fluid and compressed into a usable gas phase before it reaches the diver's lungs. This happens in a second membrane stage, a degassing module, where the oxygen-rich PFC fluid passes along one face of a hydrophobic membrane, and a partial vacuum on the gas side pulls the dissolved oxygen across into a gas stream. That gas stream feeds a small buffer reservoir, typically 2 to 3 liters of volume, that smooths out the pulsatile delivery. The diver breathes from the buffer through a standard closed-circuit rebreather loop, which scrubs exhaled carbon dioxide with a lithium hydroxide or soda-lime chemical bed and recirculates the remaining gas back to the breathing circuit. The PFC fluid itself deserves a moment of attention, because it is the component that most people are unfamiliar with. Perfluorocarbons are a class of fluorinated hydrocarbon fluids in which every hydrogen atom has been replaced by a fluorine atom. This molecular structure makes them extraordinarily chemically stable. They do not react with oxygen, they do not oxidize, they do not degrade, and they do not interact with biological tissues. They dissolve oxygen physically, not chemically, which means the oxygen comes back out of solution just as easily as it went in. The most common PFC used in medical and research applications is perfluorodecalin, which dissolves oxygen at roughly 40 to 50 volume percent, meaning 1 liter of PFC can hold nearly half a liter of dissolved oxygen. That is the carrying capacity that makes the extraction loop work. Every one of those components, the axial flow impeller, the hollow fiber membrane contactors, the PFC recirculation loop, the degassing module, the rebreather scrubber, exists as a commercial or near-commercial product today. None of them was invented for this project. The project is an integration exercise, not a materials science breakthrough. That is both encouraging and sobering. Encouraging because the components are real. Sobering because integration exercises at this scale, for a life safety application, in a marine environment, are genuinely hard. Part 4. The tow sled. Why the architecture matters. The design decision that resolves most of the engineering tension in this system is one that took the longest to arrive at clearly. Stop trying to put everything on the diver's back. The original conception of an artificial gill, going back to every version of the idea since the 1960s, imagines a device the diver wears. A vest. A panel. Something integrated into the exposure suit. The appeal is obvious. A wearable device is elegant, unobtrusive, gives the diver full freedom of movement. Every concept sketch you have ever seen of an artificial gill shows it as a vest or a backplate. That is what the imagination produces when it pictures the idea. The problem is equally obvious once you confront the physics. The water flow rates required to support human exertion cannot be generated by passive motion through a vest-sized surface at diving speeds. You need a pump. A real pump with real power draw running continuously, and the battery to run that pump for 8 hours at exertion rates does not fit in a vest. You can fit a 30-minute battery in a vest. You can fit a 1-hour battery in a vest with difficulty. You cannot fit an 8-hour battery in a vest. The energy density of current lithium polymer cells is roughly 200 watt-hours per kilogram. An 8-hour, 300-watt draw requires roughly 12 kilowatt-hours, which is 6 kilograms of battery cells alone. Before you add the pump, the membrane modules, the PFC fluid, the housing, the buoyancy compensation. You are at 20 kilograms before you finish, and 20 kilograms on a diver's back in addition to their existing gear is not a wearable system. It is an encumbrance that makes diving more dangerous, not less. The tow sled solves this without apology. The sled is a neutrally buoyant hydrodynamic housing, cylindrical, roughly 60 centimeters in diameter and 120 centimeters long, tethered to the diver on a 2-meter umbilical that carries the breathing gas supply. The sled contains the pump, the battery pack, the primary membrane extraction modules, the PFC recirculation loop, the degassing stage, and the gas buffer reservoir. The diver carries only the rebreather loop, the carbon dioxide scrubber canister, and the emergency bailout cylinder on their back. The umbilical carries oxygen-enriched gas from the sled to the diver's breathing circuit. The sled's hydrodynamic shell is designed so that the diver's forward motion assists the water intake. The sled is oriented so that the diver is essentially pulling a device that scoops water into its intake as they swim. At moderate swimming speed, the diver's motion contributes meaningfully to the water flow rate, reducing the pump workload and extending battery life. This is not a trivial effect. At 1 meter per second swimming speed, the dynamic pressure at the intake is enough to contribute 20 to 30% of the required flow, which means the pump only needs to make up the difference. Over an 8-hour mission, that is a significant battery savings. 6 brushless underwater thrusters mounted in a vectored configuration allow the sled to maintain station relative to the diver during stops, hovering maneuvers, or current crossings. A Doppler velocity log, the same category of navigation sensor used in autonomous underwater vehicles, gives the sled's control system accurate velocity and position data relative to the bottom, allowing the thruster array to compensate automatically for current without requiring the diver to actively manage the sled's position. When the diver stops to work on something, the sled holds station 2 meters behind them. When the diver swims, the sled follows. When the current shifts, the sled compensates. The diver does not think about the sled. They think about the mission. The umbilical is the system's critical interface. It carries breathing gas at controlled partial pressure from the sled to the diver. It also carries the diver's exhaled gas back to the sled's carbon dioxide scrubber, closing the rebreather loop. The umbilical is designed with sufficient slack to allow full freedom of diver movement within a 5-meter radius of the sled's hover position. For long-distance swimming, the diver clips the umbilical short, and the sled follows on a tight tow. The umbilical is armored and designed to fail safe. If it separates, the diver's bailout pack takes over automatically, and the sled's gas delivery shuts down to prevent pressure spikes. The emergency bailout backpack the diver carries is a conventional closed-circuit rebreather with a 2-hour gas supply at exertion rates. If the sled fails, pump failure, battery depletion, umbilical separation, membrane rupture, the diver switches to the bailout pack and ascends. The transition is a single valve turn. No emergency procedure more complex than that is required. 2 hours of emergency gas is more than enough time to ascend from any operational depth the sled is rated for, with decompression stops if required. The system does not eliminate the concept of a finite gas supply. It extends the operational duration from 47 minutes to 6 to 8 hours, with a 2-hour emergency reserve, at the cost of towing a sled. For the military diving applications this system is designed for, long-duration reconnaissance, covert hydrographic survey, underwater infrastructure inspection, that trade is not merely acceptable. It is mission-enabling in a way that no existing technology can match. Part 5. What this technology actually enables. Before we get to the first experiment, I want to spend a few minutes on what happens if it succeeds. Not as a sales pitch, as a technical preview of where the same core hardware leads when you scale it. The hollow fiber membrane contactor and the PFC recirculation loop are not a product. They are a platform. The tow sled is the first product that platform enables. It is not the only one. The second application is aquaculture. Fish farms, whether open water pen farms or land-based recirculating aquaculture systems, have a constant dissolved oxygen problem. Fish at commercial stocking densities consume oxygen faster than passive surface exchange replenishes it. The standard solution is electric aerators that inject compressed air bubbles into the water column. They are energy intensive, and they are inefficient. Most of the oxygen in those bubbles escapes to the atmosphere before the fish ever absorbs it. Oxygen utilization is typically 10 to 20%. The rest is wasted. A membrane aeration system running the same hollow fiber hardware in reverse, injecting oxygen-enriched gas into the water through the membrane surface rather than extracting it, achieves oxygen utilization rates of 85 to 95%. No bubbles, no surface agitation, no acoustic stress on the fish. The gas dissolves directly at the membrane-water interface and disperses by diffusion. At current electricity prices, a modular membrane aeration system for a 500 metric ton annual salmon operation pays for itself in under 3 years through energy savings alone. The hardware is the same hardware that goes in the sled. The application is different. The revenue stream is real, it is recurring, and it does not depend on a military procurement cycle. The third application is offshore infrastructure inspection. Offshore oil platforms, submarine pipelines, wind farm cable arrays, and port infrastructure all require regular underwater inspection and maintenance. Currently, work at 30 to 80 meters depth requires either saturation diving systems, which cost $50,000 per day to mobilize and operate, or remotely operated vehicles that cannot perform fine manipulation tasks. A diver with a tow sled operating at that depth range for 6 to 8 hours continuous changes the economics entirely. The saturation diving system's primary advantage is bottom time. The sled removes that advantage. A single diver with a sled can do in one deployment what currently requires a saturation team, a support vessel, and a multi-week commitment. The fourth application is autonomous underwater vehicle recharging. The Navy's Manta Ray program and similar AUV initiatives are developing long-duration underwater vehicles for surveillance and survey missions. Those vehicles currently have to surface, or be recovered by a support vessel, to recharge their batteries. A seabed-mounted docking station powered by a membrane extraction fuel cell could recharge AUVs in the field, extending their mission duration from days to months. The membrane hardware is the same. The application is different. The strategic value is substantial. The fifth application is small underwater research stations. Permanently deployed monitoring platforms, temporary hyperbaric work shelters for construction projects, and eventually manned research habitats. The Aquarius Reef Base, operated by NOAA, off the Florida Keys for over 20 years, was decommissioned in 2012. Not because it stopped being scientifically valuable, but because the operating cost of maintaining its compressed gas supplies from the surface was too high. A membrane-aerated habitat at equivalent depth runs on grid power from a seabed cable. The logistics chain that made Aquarius expensive disappears. We will come back to this in Script 3, because it is the door that leads to the long-range vision. I name these applications here because they are what makes the investment in Phase 0 rational. The total addressable market for military diving alone is small. The total addressable market for military diving, plus aquaculture, aeration, plus offshore inspection, plus AUV recharging, plus undersea habitation is not small. It is a multi-billion-dollar addressable space across 5 verticals, all served by the same core hardware validated in one benchtop experiment. The same $150,000 experiment that validates the sled opens every one of those doors. Part 6. The first experiment. What would actually prove this works? This is the part of the story that I think matters most, and that most versions of the artificial gill concept skip entirely. A concept without a falsifiable first experiment is not an engineering project. It is a thought experiment. The value of this particular idea, and the reason it is worth taking seriously rather than dismissing as another perennial pipe dream, is that the first experiment is bounded, affordable, and has a clear binary outcome. The Phase 0 prototype is a benchtop device. It does not go underwater. It does not support a human. It has one job: to demonstrate that a dual-stage hollow fiber membrane contactor system, running a recirculating perfluorocarbon emulsion as the intermediate oxygen carrier, can extract dissolved oxygen from an aerated seawater source at a rate sufficient to sustain the metabolic demand of a test animal in a sealed chamber. The test animal is a rat. A rat at moderate activity consumes oxygen at a rate that, scaled to body weight, is proportionately similar to a human diver at rest. If the membrane system can keep a sealed rat chamber at a stable oxygen partial pressure for 4 continuous hours without any compressed gas supply, extracting all the oxygen the animal consumes, in real time, from recirculating aerated seawater, the concept is validated at the biological interface. That is the gate. Not human scale, not underwater, not military rated. Just, does the extraction rate close the metabolic loop on a living mammal, continuously, without surface supply? The benchtop rig costs somewhere between $100,000 and $150,000 to build at university laboratory pricing. That includes the membrane modules, the PFC recirculation loop, the peristaltic pumps, the dissolved oxygen sensors, the sealed metabolic chamber, the data acquisition system, and the labor to build and run it. It is an ONR SBIR Phase 1 budget, the exact category of early-stage technical validation that the Small Business Innovation Research Program was designed to fund. The experiment takes approximately 6 months to design, build, and run once the funding is in hand. The outcome is unambiguous. Either the oxygen partial pressure in the animal chamber stays within the survivable window for 4 hours, or it does not. There is no interpretation required. The physics either closes, or it does not. The data is a graph of oxygen partial pressure versus time. Stable line means yes. Declining line means no. If it closes, the project advances to Phase 1, a human-scale prototype sled rated for pool testing, funded at the ONR SBIR Phase 2 level, approximately $1.5 to $2 million. If it does not close, the project stops, the data is published, and the engineering community learns exactly where the gap is. Either outcome is scientifically and economically valuable. Part 7. The honest case for why this is worth doing. I want to close with the honest version of the argument, not the promotional one. The tank on a diver's back holds 47 minutes of air. That number has not changed since 1943. Every improvement in diving equipment for the last 80 years has been at the margins. Lighter tanks, better regulators, more reliable computers. But the fundamental constraint, the countdown clock, has been untouched. What has changed in the last 20 years is not the physics. The physics has not changed. What has changed is the hardware. Hollow fiber membrane contactors have been refined by 20 years of industrial deployment. Perfluorocarbon emulsion chemistry is mature from medical applications. Brushless underwater thrusters have been commoditized by the consumer drone industry. Lithium polymer batteries have gotten dramatically better. Doppler velocity logs have shrunk from submarine scale to palm-sized. The components that were unavailable or prohibitively expensive when Aquanautics shut down in the 1980s are now available off the shelf. The integration challenge remains. But the integration challenge is an engineering problem, not a physics problem. And engineering problems yield to money, time, and focused effort in a way that physics problems do not. $150,000 and 6 months of laboratory time will tell us whether the metabolic loop closes on a living mammal. If it does not, we will have learned something important and we will stop. If it does, we will have taken the first step toward the device that makes the 47-minute ceiling a historical footnote. That is the project. Not a promise. A bet, with defined odds, a defined cost, and a defined first card to turn over. By CJ Run at Twitstrom, look, listen, or read in order to CJ Run, End, Eternal Aqualung. Script 1, The Skeptic's Journey, Richard CJ Young, C. Jung.